This time we're going to continue our work with Euler's identity that we proved in the last video and look at a particular case where the argument of this complex number happens to be equal to pi. So our complex number would be at this point on the unit circle. Now you might already guess that if the complex number is here, it would have a value -1 on the real axis with no imaginary part. But let's do the substitution and confirm that. So letting the angle theta equal pi and substituting into Euler's identity. And remember, this works with any particular angle for the argument, anything at all. We would find in this case e to the power of I pi equals cosine of pi plus I sine pi. E to the power of I pi. So using our trig, cosine of pi equals -1, sine of pi equals 0, so 0 times I is nothing, and this is Euler's formula, sometimes referred to as his formula. It's also commonly expressed as e to the power I pi plus 1 equals 0. Now some people say that's because it avoids the use of a distasteful negative number, but I prefer to think of it as involving, this version involves 5 of the most fundamental numbers in all of mathematics. 0, 1, e, the base of the natural log, I, the imaginary number, and pi, the famous constant of the circle.